What if I told you the biggest obstacle keeping quantum computers from transforming your life, a problem researchers assumed would take decades to crack, was just blown wide open by a team at the University of Chicago? And what if the fix they discovered is so clean, so deceptively simple, that you'll wonder why no one approached it this way sooner? This isn't a minor update. This isn't a small tweak. This is the kind of breakthrough that redraws timelines, reshapes whole industries, and makes every expert in the field stop and reconsider everything they assumed about when quantum computing would actually become real and practical. So stick around, because what you're about to hear is one of the biggest science stories of this decade. To grasp why this discovery matters so much, you first need to understand the core nightmare that's haunted quantum computing since the beginning. A quantum computer isn't like the laptop on your desk or the phone in your pocket. Those machines run on ordinary bits, tiny switches that are either on or off, 1 or 0. A quantum computer runs on something entirely different called qubits, and qubits can exist in a state called superposition, meaning they can be 1 and 0 simultaneously. That sounds impossible, but it's real, and it's exactly what gives quantum computers their extraordinary power. Because when qubits sit in superposition and are linked through a quantum property called entanglement, a quantum computer can explore millions of possible answers to a problem all at once. A normal computer has to check answers one at a time. A quantum computer can check them all together. The potential here is staggering. We're talking about designing new medicines that could treat diseases we currently can't even slow down. We're talking about cracking the encryption that protects nearly every bank transaction, every private message, and every government secret on Earth. We're talking about tackling climate challenges, streamlining global supply chains, and supercharging artificial intelligence to a degree that would make today's AI look like a pocket calculator. Quantum computers aren't just computers. They're a fundamentally different kind of thinking machine. And for decades, scientists were confident we were still at least 30 years away from building one strong enough to actually pull any of this off. Here's why. Qubits are unbelievably delicate. On a normal computer, the bits hold steady. They don't randomly flip from 1 to 0 just because someone walked by too quickly. Qubits, though, are nothing like that. They're so sensitive to their surroundings that a slight shift in temperature, a vibration, electromagnetic noise, even a stray nearby particle can knock a qubit out of its quantum state and trigger an error. Scientists call this decoherence. And since quantum calculations involve billions of individual qubit operations, even a minuscule error rate snowballs into total failure. You end up with a computer you can't trust to give you a correct answer. And a computer that can't give correct answers isn't really a computer. It's an expensive science experiment. To put a number on this fragility, today's best quantum computers have physical qubit error rates around 1 in 1,000 per operation. That sounds tiny until you realize a useful quantum algorithm might need billions of operations. If each one carries a 1 in 1,000 chance of failing, the odds of your whole computation coming out correct shrink to almost nothing. It's like building a skyscraper out of bricks that each have a random 1 in 1,000 chance of crumbling on any given day. The structure would collapse before you got 3 floors up. That's the real scale of the error problem in quantum computing. So engineers came up with something called quantum error correction. The concept is simple, even though pulling it off is brutally hard. If you can't stop errors from happening, you need to catch and fix them as they occur. The method is to take the information held by one logical qubit and spread it across many physical qubits. So instead of a single qubit carrying one piece of information, you might have hundreds or thousands of physical qubits acting together as one dependable logical qubit. When one of those physical qubits slips up, the others can spot it and correct it automatically. It's the quantum equivalent of backing up your important files in 3 separate places, so losing one hard drive doesn't mean losing everything. And here's where the real trouble starts. If it takes 1,000 physical qubits to form a single reliable logical qubit, and a useful quantum algorithm needs thousands of logical qubits to run, then you need millions of physical qubits before the machine can do anything meaningful. Right now, the most advanced quantum computers on the planet have only a few thousand qubits at best. IBM's strongest machine has around 1,000. Google's systems are in the same range. We were talking about needing to scale up by a factor of 1,000 or more just to reach the starting line of real usefulness. That's why experts kept saying 30 years. That's why the timeline felt so discouraging. The hardware kept improving, but the overhead from error correction was so massive that every step forward felt like 2 steps back. If this is blowing your mind the way it's blowing mine, Go ahead and hit that like button and subscribe right now, because this is exactly the kind of content the algorithm buries unless you tell it you want more. So here's what the University of Chicago team did, and here's why it changes everything. Researchers at the Pritzker School of Molecular Engineering published a breakthrough in Nature Physics that tackles the error correction overhead problem from a completely different angle. For decades, the go-to method for quantum error correction relied on something called surface codes. In a surface code, each logical qubit is protected by arranging a large number of physical qubits in a two-dimensional grid. To catch errors, each qubit only checks in with its immediate neighbors. The issue is that this neighbor-only setup is wildly inefficient. You need a massive number of qubits just to get decent protection. Picture a neighborhood watch where everyone can only keep an eye on the two houses right next to them. If something happens 3 streets over, nobody in the watch notices. The coverage is local and costly, and you'd need an enormous number of participants to cover an entire city. Instead, the University of Chicago team built a new blueprint using something called quantum low-density parity check codes, or QLDPC codes. The key difference is huge. With QLDPC codes, qubits don't just check in with their immediate neighbors, they compare notes with qubits far away, scattered across the whole system. Going back to the neighborhood watch idea, it's like handing everyone binoculars and a radio so they can monitor and talk to people clear across town. Suddenly you need far fewer people to cover the same ground. The whole system becomes dramatically more efficient. This long-range checking lets the system catch and fix errors using far fewer physical qubits per logical qubit. Information gets encoded more efficiently, redundancy drops, and you can hit the same level of error protection with a fraction of the resources. Researchers had known for years that QLDPC codes were theoretically better than surface codes. The math left no doubt. So why wasn't anyone actually using them? Here's the catch that had kept QLDPC codes on the shelf. Comparing qubits that are far apart requires those qubits to communicate across long distances inside the hardware. But in standard quantum hardware, qubits are fixed in place. They sit where they sit and can only talk to their immediate neighbors. Getting 2 qubits on opposite ends of a chip to communicate was considered nearly impossible without introducing new, worse errors. This long-distance communication problem was the wall blocking QLDPC codes from being practical for years. Everyone knew they were theoretically superior. Nobody could figure out how to make them physically work. It was like spotting a faster route on a map, only to realize the shortcut runs straight through a mountain nobody had tunneled through yet. The University of Chicago team solved it with a hardware trick that's almost elegant in its simplicity. They proposed using reconfigurable atom arrays. Instead of fixed qubits locked onto a silicon chip, they use neutral atoms held in place by lasers. And because these atoms are suspended by light rather than embedded in solid material, they can actually be moved. You can pick up an atom with a laser and carry it to a new spot inside the quantum processor. So when the QLDPC code needs 2 distant qubits to talk, you don't move the information, you move the qubit itself. You physically carry the atom to where it needs to be, let it interact with its partner, run the error checking step, then send it back to its original spot. The long-distance communication problem vanishes, because distance stops mattering once you can simply relocate the players. When the team paired QLDPC codes with this reconfigurable atom array hardware, the results were jaw-dropping. With this new blueprint, a quantum algorithm needing thousands of logical qubits could potentially run with fewer than 100,000 physical qubits. Compare that to the millions that would be required under the old surface code approach. That's a 10 to 20-fold cut in the total number of qubits needed to reach the same computing power. And that's not a small win. That's the difference between a machine that's achievable in a few years and one that might not exist until your grandchildren are grown. A revolution within your lifetime, and we're just getting started. Now let's talk about what this actually means in the real world, because the implication is that the timeline for useful quantum computing just collapsed. Experts who used to say 30 years are now having to revise that number. The engineering challenge shifts dramatically. Instead of needing to build and control millions of qubits, you need to build and control tens of thousands. That's still incredibly hard, but it's the kind of hard that might actually get solved in the next several years instead of the next several decades. The second consequence touches drug discovery, and this one could genuinely save millions of lives. One of the most computationally brutal problems in biology is simulating how molecules interact at the quantum mechanical level. When developing a new medicine, you need to understand precisely how a drug molecule will bind to a protein target in the human body. That involves quantum-level interactions so complex that even the world's most powerful classical supercomputers can't model them accurately beyond very small molecules. As a result, pharmaceutical companies spend billions of dollars and 10 to 15 years on average just to take a single drug from initial discovery to market. And most drug candidates fail in clinical trials because earlier simulations weren't precise enough to predict how the drug would behave in an actual human body. A fault-tolerant quantum computer could simulate these molecular interactions with genuine quantum mechanical accuracy. It could predict how drug molecules interact with proteins, enzymes, and cell receptors, potentially shrinking development timelines from 15 years down to maybe 3 or 4. It could let scientists screen millions of candidate drugs in flawless simulation before ever synthesizing a single molecule in a lab. Diseases with no current treatment, conditions killing people right now, could end up with multiple validated treatment options within a decade of fault-tolerant quantum computers becoming a reality. The amount of human suffering this technology could prevent is almost too vast to wrap your head around. The third consequence is one that should concern everyone right now: encryption. Nearly every piece of sensitive data sent across the internet today is protected by encryption built on one simple mathematical fact. Factoring extremely large numbers into their prime components is computationally out of reach for classical computers once the numbers get big enough. Your bank relies on this. Your messaging apps rely on this. Medical records rely on this. The entire digital economy is built on this assumption. A quantum computer running an algorithm called Shor's algorithm could, in theory, break RSA encryption, the most widely used encryption standard in the world. The national security stakes are serious enough that the US government has funded a separate research effort to build post-quantum encryption standards. The fact that fault-tolerant quantum computers may now arrive far sooner than expected turns this from a distant worry into an urgent one. Now go ahead and smash that like button and hit subscribe, because the next few years of quantum news are going to move faster than almost anything we've seen in the history of computing. Beyond medicine and cryptography, the ripple effects reach into climate science, materials science, and artificial intelligence itself. Quantum computers could model new materials at the atomic level, leading to breakthroughs in superconductors, more efficient solar cells, and better battery technology that could reshape clean energy. They could optimize global logistics networks with a precision that saves huge amounts of fuel and meaningfully cuts carbon emissions. They could speed up the training of AI models. This isn't just an upgrade to existing tools, it opens up entirely new categories of scientific capability that simply don't exist yet. Let's also recognize why the University of Chicago has become one of the centers of this revolution. The Pritzker School of Molecular Engineering was built from the ground up to bring together different scientific disciplines: physicists, chemists, computer scientists, and engineers, all in one environment designed specifically for cross-disciplinary work on quantum hardware and theory. The team behind this breakthrough, led by Professor Liang Jiang, included collaborators from Harvard, Caltech, the University of Arizona, and Quira Computing. The involvement of Quira, an actual quantum hardware company building atom-array quantum computers, matters a lot. It means there's already a direct line from this academic discovery to real engineering development. This wasn't a theoretical exercise sitting in a vacuum. This was a full system design built by both the scientists and the people who will actually construct it. Now, let's be honest about where things really stand, because intellectual honesty matters here. As of this recording, the University of Chicago's framework is a theoretical blueprint. The reconfigurable atom array hardware itself is real and actively being developed by Quira and others. But combining QLDPC error correction with movable atom systems at the scale needed for practical computing hasn't yet been fully demonstrated in a working machine. It's a target the field is now chasing with far more confidence than before. What makes this work so important is that it offers a clear, realistic engineering path. Before this, researchers knew QLDPC codes were theoretically superior, but had no practical way to build them. The Pritzker team handed them that blueprint. And once you have a real plan, you can start building. To put this in the widest possible context, think about what the invention of the transistor meant for human civilization. When it was invented in 1947, nobody could have predicted how the relentless miniaturization of transistors would go on to transform medicine, communication, science, entertainment, and basically every part of how humans live. We're at the very start of an equivalent turning point. Error correction has been the first major wall standing between quantum computing and practical reality. The University of Chicago's QLDPC breakthrough isn't a magic wand that makes the wall disappear overnight, but it reveals a door in that wall that nobody had clearly spotted before. And once you know where the door is, you can walk through it. Professor Fred Chong of the University of Chicago, one of the most respected voices in quantum computing, described this moment using the phrase escape velocity. What he means is that quantum computing has crossed a threshold where progress is now feeding itself and accelerating. The hardware is good enough, the error correction is efficient enough, and the engineering know-how is mature enough that building a genuinely useful quantum computer is no longer fundamentally a physics problem, it's an engineering problem. And engineering problems have clear paths to a solution once you've got enough resources, talent, and time. The QLDPC breakthrough is a massive piece of that engineering path. This breakthrough doesn't exist in isolation either. In the years surrounding this work, there's been a wave of major advances across the quantum industry. Google demonstrated below-threshold error correction with its Willow chip, proving that scaling up a quantum system can actually shrink the error rate instead of growing it, which is the fundamental requirement for real fault tolerance. IBM announced new error-correcting codes that significantly cut the qubit overhead needed for fault-tolerant computing. Several other companies, including Microsoft, Quantinuum, IonQ, and QEra, have each announced their own major advances. The quantum community is living through a genuine revolution on multiple fronts at once, and the University of Chicago's work is one of the most important pieces of that bigger picture. For you, living through this historic moment, there are a few takeaways worth holding on to. If you work in a field tied to digital security or encrypted data, the push to move toward quantum-resistant encryption is real and growing fast. If you're in medicine or biotech, the pace of drug discovery you'll see over the next 15 years might make the last 50 years look slow by comparison. And if you're simply a curious person trying to understand where the world is heading, the answer is that we're closer than ever before to a true quantum advantage, the moment when a quantum computer solves a real-world problem that no classical computer could ever crack in a useful amount of time or at a reasonable cost. The University of Chicago found the shortcut quantum computing has needed for years. Not a shortcut that skips the hard work, a shortcut that makes the hard work achievable on a human timescale. They cut the requirement from millions of components down to tens of thousands. They showed how shuttling atoms around with lasers could solve a communication problem that fixed hardware never could. They turned a 30-year timeline into something the next decade might actually deliver. And they pulled it off by blending deep theoretical insight with hands-on engineering creativity, the kind of result that only happens when the right people come together in the right setting with the right vision. Quantum computing has been promised for decades. It's been overhyped, underhyped, written off, and celebrated in cycles. But what's different now is that we've moved past asking whether it will happen to asking when. And the answer to when is no longer a number that makes people sigh and look away. It's a number that's getting engineers to start building, investors to start committing, and governments to start preparing. The mountain is still there, but Basecamp just moved 3/4 of the way up. Hit like, subscribe, and stay close, because this story is just getting started, and you don't want to miss what comes next.